welcome back. I'm Mahnur, and today we will be continuing on with the chapter of kinematics. Now, last time we had discussed some fundamental terms of this entire chapter, and those we called the ABCs of this entire chapter. With that knowledge, we are now well equipped in diving further into this topic. To do that, we must remind ourselves of the main goal of this entire chapter, which is to know how to study motion. Now, it could be of any kind of object. It could be this object sliding up and down the slope, or even of a rocket ship launching up in space. No matter what kind of motion you're studying, there are always two approaches you could take, either a quantitative one or a qualitative. In a quantitative approach, you want your final answer to be numerical, or you're dealing with numbers, in which case you would primarily be focusing on equations. But if you're taking a qualitative approach, you're dealing with anything but numbers, in which case you're always using diagrams to get your analysis. Now, when it comes to the graphs of kinematics, there are two types that we should be familiar with: displacement versus time and velocity versus time. Now, proceeding onwards, we will be looking at each of these types of graphs one by one and see some important features of each of these graphs, so that we can evaluate some important pieces of information from these diagrams. So let's start off with the displacement versus time graph. Here we have displacement on the y-axis and time on the x-axis. Now suppose for some kind of a moving object, you evaluated the following kind of graph line. What's one feature you can think of that we can evaluate over here? An obvious guess would be its gradient, right? In which case, what we could do is take 2 points and construct a gradient triangle like the one shown here and use it to evaluate gradient. For that, what we would do is dividing the change along the y-axis with the change along the x-axis, represented here as delta y divided by delta x. Now, since we have displacement on the y-axis and time on the x-axis, we can replace delta y with delta s and delta x with delta t. What we've evaluated here is the definition and equation for velocity, which helps us conclude that for a displacement versus time graph, the gradient represents velocity. Now let's move on to the velocity versus time graph, where we have velocity on the y-axis and time on the x-axis. Now, let's suppose we have yet another graph line evaluated on this graph. Once again, we can measure its gradient, and we'll take the same approach as before. Take 2 points, construct a gradient triangle like the one shown here, and then use it to evaluate the gradient as per usual. Delta y divided by delta x. This time, we have velocity on the y-axis and the usual time on the x-axis, in which case we can replace delta y with delta v and delta x with delta t. Now what we have recreated is the definition and equation for acceleration. So what we conclude here is that for a velocity versus time graph, the gradient represents its acceleration. One other feature we can look at for a velocity versus time graph is the following. This time the graph line is a horizontal line instead of a common tilted one. What this means physically is that with the passage of time, the object's velocity is not changing. In other words, the object is moving with constant velocity. Now suppose we take some 2 points which represent a time interval delta t on the x-axis and a value of velocity v on the y-axis. We take a shaded region like the one shown here, and we wish to evaluate the area underneath the graph. For that, we would use a typical formula for a rectangle, length times breadth. If we analogize it with the graph that we have on the left-hand side, we would conclude that the length is equal to the velocity v and breadth is equal to delta t. If we combine the two, we get a result that claims that the area equals velocity multiplied by time interval delta t. This is nothing but a rearranged version of displacement, which helps us conclude that for a velocity versus time graph, the area underneath the graph actually represents displacement. And this conclusion is so special, in fact, that it's true for any kind of shape out there. Now we have reached our second checkpoint, where we primarily discussed the graphs of kinematics, and there were two types that we can review. displacement versus time, and velocity versus time. For displacement versus time graphs where we had displacement on the y-axis and time on the x-axis, we claim that the gradient represents velocity. On the other hand, for a velocity versus time graph where we had velocity on the y-axis and time on the x-axis, here the gradient represented acceleration and the area underneath the graph represented displacement. Thank you.